Again, this is the hardest concept I teach at Bidwell. If it's not quite clear to you, it's fine. Hopefully you get something out of it. But here we go. This is Archimedes' principle. So just as an intro, so here's a swimming pool, right? And you have your shallow end and your deep end. And most of you know that the deeper you go in the water, the higher the pressure is, right? So if you're swimming at the bottom of the pool here, your ears might hurt because the pressure is higher, but they won't hurt as much here because it's shallower. And the reason why that is the deeper you go, the more water that's sitting on top of you, right? I mean, this water is super heavy, right? So the deeper you go, the more water you have actually pushing down on you. Now this arrow should look familiar. In the last video, we were talking about weight as being a force pushing down, right? So this weight is sitting on top of you, and here you don't have as much water sitting on top of you, so the pressure is less. And that's where the pressure thing comes in from the previous video. We have pressure sitting on top of you, more pressure because there's more weight of the water pushing down on you. Okay, so in terms of atmospheric pressure, right? You have here's your atmosphere. You have a mountain, right? So you have this much pressure sitting on top of you when you're at the top of the mountain, and you have this much atmosphere sitting on top of you when you're at sea level. And that's why when you're going up into the mountains or down into the sea level, your ears start to pop because you have less atmosphere sitting on top of you here and more sitting on you here. It's the same principle inside of a pool. Right now, in terms of how things float and sink, you can think of, here's my beaker, and I have an object in the water. I'm just going to put it right here. Okay. Now, the amount is really low, but there is a difference between the pressure on this object in the beaker. There is a difference between the pressure here and the pressure here. The pressure at the bottom of the object is going to be high, and the pressure at the top is going to be lower. I'll say higher. The pressure on the bottom is going to be higher than the pressure on the top. Even as something as small as a beaker, it's still going to be higher at the bottom than it is on the top. And what that pressure does is it pinches at the bottom. It pinches the object at the bottom and makes it want to go up. Okay, so how much that force is, like how that pressure that's pushing on the bottom, that is going to produce a force pushing up. Okay, now there's also gravity pushing down or pulling down on the object. Okay, so this force pushing up is called the buoyant force. And this is the gravity force, or the weight. Okay, if the buoyant force is higher than the weight of the object, the force pulling down, if the buoyant force is higher than the weight force, I'll say weight force. Okay, if the buoyant force is higher than the weight force, then it's going to push it up and the object's going to float. If the weight more than the buoyant force, it's going to sink. Okay, now we've already calculated a weight force in the previous videos. You can calculate the buoyant force, and that's what Archimedes' principle is calculating the buoyant force on an object. And this is how it works. This is really tricky. Okay, so you're going to have to, if you want to get this, you're going to have to really want to get it. So I have my beaker again, and I have my object, and let's say that this object takes up 15 milliliters of space. Okay, so this object right here has a volume of 15 milliliters. The buoyant force pushing up on this object, the buoyant force, is equal to the weight of how much water gets pushed out of the way by the object or displaced by the object. Okay, so we need to calculate how much weight this much water is. How much does this much water weigh? Well, water, we know, is 1 gram per milliliter, right? That was our density. It's 1 gram per milliliter. So if I've got 15 milliliters, I've got 15 grams. That 15 grams can be converted into kilograms. And now we have all the numbers we need to calculate the weight of that much water. I've got the mass times the acceleration of Earth's gravity. So this is 0.015 kilograms. The acceleration of Earth's gravity is 9.8 meters per second squared. We're in a room. And the force would be 0.015 times 9.8. Oops. 0.015 times 9.8. 0.15. So 0.15 newtons. This is the buoyant force. It's the weight of the water that this object pushes out of the way or displaces. So this upward force is 0.15 newtons. If this object's weight outside of the water is higher than 0.15 newtons, it's going to sink. If the object's weight is less than 0.15 newtons, that means the buoyant force is higher than the weight force and it's going to float. Okay, so I am going to stop the video there, and then I'm going to give you some problems to try with some, it'd be a lab that we would have done for Archimedes principle. Okay, so I know this is taking a while. Again, this is one of the hardest things. Hopefully I see you in video 4. This is going to be a slog. Okay, thanks for watching.